Welcome to Whispering Atom, where curiosity finds its quiet voice and science becomes a gentle companion for rest. I'm so glad you've joined me tonight for this peaceful journey beneath the waves, where we'll discover together why the deep sea holds onto its darkness like a secret whispered between old friends. As you settle in wherever you are in this wide world, I'd love to know where you're listening from tonight and what time it is in your corner of the universe. Are you watching from a cozy bedroom as evening settles in? Perhaps from a quiet living room where the day's last light filters through your windows? Or maybe you're somewhere where dawn is still hours away and the night wraps around you like a familiar blanket. Take a moment, if you'd like, to share in the comments below where you are and what time your clock shows right now. There's something wonderfully comforting about knowing we're all here together, scattered across time zones, but united in this gentle exploration of our planet's most mysterious spaces. Now, get comfortable. Adjust your pillows, pull that blanket a little closer, let your shoulders drop just a bit. Take a slow, deep breath and feel yourself settling into this moment. Tonight, we're going to dive not with the rush of adventure, but with the gentle curiosity of someone following a path through a peaceful forest. We're going to explore one of the most beautiful mysteries of our planet, why the deep ocean remains forever dark, no matter how brilliantly the sun shines above. Imagine, if you will, that you're standing at the edge of a vast ocean on a perfectly clear day. The sun hangs bright and warm above you, casting everything in golden light. The waves lap gently at your feet, and the water stretches out before you, shimmering and blue, extending all the way to the horizon where it meets the sky in a soft, blurred line. From where you stand, the ocean appears to be filled with light, dancing and sparkling as if thousands of tiny mirrors were floating just beneath the surface. You might think, looking at this beautiful scene, that surely this light penetrates deep into the ocean. After all, you can see through the water near the shore. You can watch fish swimming several feet down, seashells, and sand on the bottom. Observe the way the sunlight creates shifting patterns on the seafloor. The water seems so clear, so transparent, like liquid glass. How could something so see-through possibly block the sun's powerful rays? And yet, if you could somehow travel down through this water, moving deeper and deeper beneath the surface, you would discover something quite remarkable. You would find that the ocean has layers, like a gentle gradient of light that slowly, peacefully, fades into something far more mysterious. The bright, dancing illumination that fills the surface waters doesn't simply continue downward forever. Instead, it begins a slow, graceful retreat, leaving behind a realm of perpetual darkness that no amount of surface sunshine can ever touch. This isn't a sudden change, mind you. It's not as if you would drop through some invisible barrier and find yourself instantly plunged into blackness. No, the ocean is far more subtle than that, far more gentle in the way it transforms light into darkness. The change happens gradually, almost imperceptibly at first, like the way twilight creeps across the sky at the end of a long day. One moment you're in full daylight, and then, without quite noticing when it happened, you find yourself in evening's soft embrace. Let's begin this journey together, starting from that bright surface where the sun's rays first touch the water. Picture those countless photons, tiny packets of light energy, streaming down from our nearest star, traveling through 93 million miles of empty space to reach our planet. They've been traveling for about 8.5 minutes. These little messengers of light, racing through the vacuum at the speed of light, carrying with them all the colors of the rainbow hidden within what appears to be simple white sunshine. When these photons finally reach Earth's atmosphere, they've already begun their first encounter with matter. They bounce off air molecules, scatter through clouds, and filter through the invisible layers of gas that surround our planet. But most of them make it through, streaming downward to paint our world in brilliant light. They illuminate the trees, warm the ground, and eventually arrive at the surface of the ocean. Now, here's where our story really begins. The moment a photon touches the surface of the water, something quite extraordinary starts to happen. You see, Water isn't quite as transparent as it first appears. Oh, it's wonderfully clear compared to many substances. You can certainly see through it much better than you could see through, say, a piece of wood or a stone. But water molecules, those tiny combinations of hydrogen and oxygen that make up every drop of our oceans, have their own particular way of interacting with light. Think of it this way. If you've ever looked at the world through a piece of colored glass, you know that the glass doesn't block all light, but it does filter it, allowing some colors to pass through while absorbing others. Water does something similar, but much more subtly. It's like looking through the faintest, most delicate filter imaginable, so gentle that you barely notice it at first, but present nonetheless. As our photons enter the water, they begin to encounter these molecules, billions upon billions of them, each one capable of absorbing a tiny bit of light energy. At first, this absorption is so minimal that you wouldn't notice it at all. The water still looks perfectly clear, still seems to let all the light pass through without any trouble. You could swim down 10 feet, 20 feet, even 50 feet, and the water around you would still be filled with beautiful, bright illumination. But here's the thing about very subtle changes. When they happen over and over again, they add up. It's like compound interest, but in reverse. Each water molecule absorbs just a tiny, almost immeasurable amount of light. But when you have countless trillions of these molecules, each one taking its microscopic share, the effect begins to accumulate. Layer by layer, foot by foot, the light grows just a little bit dimmer. At first, you might notice that certain colors seem to fade more quickly than others. The warm reds and oranges that paint a sunset, the deep crimsons of autumn leaves. These colors are among the first to disappear as you move deeper into the ocean. It's not a dramatic change, not like someone suddenly turning off a red light bulb. Instead, it's like watching a watercolor painting as an artist gently washes over it with clear water, letting the pigments fade slowly and naturally until they blend into the background. This happens because different colors of light carry different amounts of energy and interact with water molecules in slightly different ways. Red light, with its longer wavelengths, is absorbed more readily by water than the cooler blues and greens. So as you descend through the ocean layers, the world around you gradually shifts from the full spectrum of sunlight towards something cooler, more blue-green, like the color of a deep mountain lake on a cloudy day. Imagine yourself floating gently downward through this transforming light. At 30 feet below the surface, you might notice that the vibrant reds have become muted, more purple. The bright oranges have softened into pale yellows. But there's still plenty of light around you, still enough illumination to see clearly, to watch the gentle movement of small fish, to observe the way particles drift like tiny stars through the water column. As you continue your peaceful descent, passing 60 feet, then 90, then beyond, the changes become more noticeable. The yellows begin to fade now, leaving behind a world painted primarily in blues and greens. It's still beautiful, still bright enough to see, but there's a sense that you're entering a different realm now, a place where the sun's influence is growing weaker, where the water itself is beginning to claim dominion over the light. This is one of the most remarkable things about the ocean's relationship with light. It's not simply a matter of the water being in the way, like a curtain blocking a window. Instead, the water is actively transforming the light, changing its very nature as it passes through. Each molecule is like a tiny artist, selectively choosing which colors to keep and which to let go, creating a masterpiece of gradual transition that spans hundreds and eventually thousands of feet. The process is so gentle, so gradual, that if you were somehow able to experience it in real time, it would feel almost meditative. There's no violence here, no sudden shock or dramatic change, just the quiet, patient work of countless molecules, each one doing its small part in the grand transformation of light into darkness. It's like watching the sun set in extreme slow motion, where each degree of the sun's descent takes not minutes, but hundreds of feet of ocean depth. And this is just the beginning of our journey. We're still in the well-lit upper layers of the ocean, still in what marine biologists call the sunlight zone, where photosynthesis can occur and where most of the ocean's visible life makes its home. Below us, far below, lie layers of water where no surface light has ever penetrated, regions of such complete darkness that the very concept of day and night becomes meaningless. But we're not rushing toward that darkness. Instead, we're taking our time, moving gently through each layer, observing how the light changes, how the water's relationship with photons creates this beautiful, gradual transition from the bright world above to the mysterious realm below. We're learning to appreciate each stage of this transformation, each subtle shift in color and brightness, like a master painter showing us how to blend one shade seamlessly into another. As we float here in this peaceful blue-green world, perhaps 100 feet below the surface, we can still look up and see the bright circle of the sun wavering above us, distorted by the water but still clearly visible. We can look around us and see fish swimming, particles drifting, the gentle movements that characterize life in the ocean. But we can also sense something else, the vast depth that lies below us, the enormous volume of water that stretches down and down toward the seafloor, each layer adding its own small contribution to the great work of transforming light into darkness. This is where our real exploration begins, not with the dramatic plunge into the abyss, but with this gentle recognition that we're witnessing one of nature's most patient and thorough processes. The ocean is teaching us something about transformation, about how even the most powerful force, the light of our sun, can be gradually, peacefully, lovingly absorbed by something as simple as water. In the chapters ahead, we'll follow this process deeper, exploring how each layer of the ocean adds its own character to the transformation of light. We'll discover the science behind this beautiful phenomenon, learn about the behavior of photons and molecules, and come to understand why no amount of surface sunshine can ever illuminate the deepest parts of our oceans. But for now, let's simply float here in this gentle blue-green light, feeling the soft embrace of the water around us, appreciating the way the sun's rays create dancing patterns that grow softer and more mysterious with each passing foot of depth. Let's rest in the knowledge that we're part of something much larger than ourselves, suspended in an ocean that stretches for thousands of miles in every direction and thousands of feet downward, all of it participating in this grand, gentle transformation of light. The water around us is comfortable, neither warm nor cool, simply present and welcoming. Small particles drift past like lazy snowflakes, catching and scattering the remaining light in tiny sparkles that appear and disappear in the slow rhythm of deep water movement. Fish move through this space with the easy grace of creatures perfectly at home in their three-dimensional world, their scales catching occasional glints of the filtered sunlight. This is a peaceful place, this layer of the ocean where light is still present but changed, where the bright energy of the surface has been transformed into something softer, more contemplative. It's a place of transition, where the familiar world above gradually gives way to something entirely different below. And it's here, in this gentle blue-green twilight, that we begin to understand the ocean's most fundamental secret, that darkness in the deep sea isn't simply the absence of light, but the result of light's own willing transformation. As we prepare to explore deeper layers in the chapters to come, we can take comfort in knowing that this process we're witnessing is one of the most stable, reliable phenomena on our planet. For billions of years since the first oceans formed on Earth, this same gentle absorption of light has been happening in exactly this way. The ocean's relationship with sunlight is one of the oldest partnerships in the history of our world, refined through countless eons into the beautiful, gradual process we're observing now. So let's rest here for a moment, floating peacefully in this blue-green light, feeling the gentle support of the water around us, appreciating the way the sun's energy has been transformed into something softer and more mysterious. Let's listen to the quiet sounds of the underwater world, the distant whisper of currents, the soft movements of marine life, the occasional gentle click or call of creatures adapted to this filtered light environment. This is our starting point for the deeper journey ahead. This place where light still exists, but has begun its transformation into something entirely different. From here, we'll follow the path of photons as they encounter more and more water molecules, as they gradually surrender their energy to the patient embrace of the ocean, as they participate in one of nature's most beautiful demonstrations of how even the brightest light can find peace in gentle darkness. Now that we've found our peaceful place in the gentle blue-green waters, let's take a moment to really understand what's happening around us. Every second, millions upon millions of tiny photons are making the same journey we're imagining, streaming down from the sun through the atmosphere and into the welcoming embrace of the ocean. These photons are remarkable little travelers, each one carrying its own packet of energy, its own story of the 8.5-minute journey from our nearest star. To truly appreciate what happens to light in the ocean, we need to think about these photons not as an abstract concept, but as real, individual messengers of energy. Picture them, if you will, like countless tiny soap bubbles drifting downward through the water, each one invisible to our eyes, but carrying within it a specific amount of energy, a specific color, a specific wavelength that determines how it will interact with the water molecules it encounters. When we speak of sunlight, we often think of it as simply white light, pure and uniform. But this white light is actually a symphony of colors, all blended together so seamlessly that they appear as one. If you've ever seen sunlight pass through a prism or noticed how raindrops can create a rainbow, you've witnessed this hidden complexity. The light streaming down into our ocean contains every color you can imagine. The deep reds of roses, the bright oranges of marigolds, the golden yellows of summer sunshine, the fresh greens of spring leaves, the cool blues of morning sky, the rich indigos of twilight, and the soft violets of distant mountains. Each of these colors represents photons with different wavelengths, different amounts of energy, and most importantly for our story, different relationships with water molecules. It's like a diverse group of travelers, each with their own personality, their own preferences, their own way of interacting with the world they encounter. Some are bold and energetic, others are gentle and subtle. Some are eager to share their energy with whatever they meet, while others are more reserved, more likely to continue their journey unchanged. As these varied photons begin their descent through the water, they start to encounter the molecules that make up seawater. Now, a water molecule is a beautifully simple structure, two hydrogen atoms bonded to one oxygen atom, creating a tiny angular shape that chemists represent as H2O. But despite their simplicity, these molecules have some fascinating properties that make them perfect partners in the dance of light absorption. Water molecules are what scientists call polar molecules, meaning they have a slight positive charge on one end and a slight negative charge on the other. This polarity gives them the ability to interact with electromagnetic radiation, which is exactly what light is. When a photon encounters a water molecule, several things can happen. The photon might pass right through, continuing its journey unchanged. It might be scattered, bounced off in a slightly different direction like a ball bouncing off a gentle slope. Or it might be absorbed, its energy transferred to the water molecule and transformed into a tiny amount of heat. The probability of each of these outcomes depends largely on the photon's wavelength, its color. Red photons, with their longer wavelengths and lower energy, are particularly likely to be absorbed by water molecules. It's as if the water has a special affinity for these warm colors, welcoming them in and transforming their light energy into the subtle warmth that characterizes the ocean's upper layers. This absorption doesn't happen all at once, of course. A single red photon might travel several feet through the water before it encounters just the right water molecule, oriented in just the right way to absorb its energy. But with billions of photons streaming downward every second, and trillions of water molecules suspended in every cubic foot of seawater, these encounters are happening constantly, creating a gentle but persistent filtering effect. Imagine yourself still floating in that peaceful blue-green light, perhaps now at a depth of about 150 feet. If you were to look around you, you might notice that the world has taken on an even more distinctly blue-green cast. The warm colors that painted the surface waters have become increasingly rare down here. It's not that they've disappeared instantly. Rather, they've been gradually absorbed, their energy lovingly accepted by countless water molecules during the long journey downward. Think of it like listening to music through a very gentle filter that slowly removes certain frequencies. At first, you might not notice the change. The melody is still recognizable, still beautiful. But as the filtering continues, as more and more of the warm, low frequencies are absorbed, the music takes on a different character. It becomes cooler, more ethereal, like the difference between a full orchestra and a flute quartet. Both are beautiful, but they create entirely different moods, entirely different atmospheres. This is exactly what's happening to the sunlight around us. The red and orange photons, those warm frequencies of the light spectrum, are being gently absorbed by the water molecules, their energy contributing to the overall warmth of the ocean. What remains is increasingly dominated by the cooler colors, the blues and greens that give these depths their characteristic hue. But the process isn't uniform across all these cooler colors either. Even among the blues and greens, there are subtle preferences. The deeper blues, those approaching violet on the color spectrum, are absorbed somewhat more readily than the brighter, clearer blues. The result is that as you descend deeper into the ocean, the light gradually shifts not just from warm to cool, but within the cool colors themselves, creating an ever more refined palette of blue-green illumination. At 200 feet deep, you might notice that the light around you has taken on an almost supernatural quality. It's still bright enough to see clearly, bright enough to read a book if you had one. But the character of the illumination is unlike anything you'd experience on the surface. It's as if you're surrounded by the gentle glow of blue-green neon, soft and even, without the harsh shadows and bright highlights that characterize surface lighting. This even diffused quality comes from another aspect of how light behaves in water: scattering. While absorption is removing certain colors from the light, scattering is spreading the remaining light in all directions. When a photon encounters a water molecule and isn't absorbed, it might be deflected at a slight angle, sent off on a new path through the water. Small particles suspended in the water, tiny bits of organic matter, microscopic organisms, dissolved minerals, all contribute to this scattering effect. The result is that the light around you doesn't come from any single direction, the way surface sunlight streams down from above. Instead, it seems to emanate from everywhere at once, a gentle, omnidirectional glow that eliminates harsh shadows and creates an atmosphere of soft, peaceful illumination. It's like being inside a perfectly designed photographer's studio, where the lighting is so carefully arranged that everything is visible and beautiful, but nothing is harsh or glaring. As we continue our gentle descent, passing 300 feet, then 400, the character of the light continues to evolve. The remaining photons are now predominantly blue and blue-green, creating an environment that feels almost otherworldly in its beauty. If you've ever been in a room lit only by blue LED lights, you might have some sense of this atmosphere, but even that doesn't quite capture the ethereal quality of natural blue-green light filtered through hundreds of feet of seawater. At these depths, something interesting begins to happen to your perception of distance and space. With the warm colors gone and only the cool blues and greens remaining, the usual visual cues that help us judge depth and distance become muted. The result is a sense of existing in an infinite blue-green space, where the boundaries between near and far become soft and undefined. It's deeply peaceful, this sensation of floating in unlimited blue space, like drifting through a cloud made of gentle light. The marine life at these depths has adapted beautifully to this blue-green world. Fish that live in these waters often have silvery scales that reflect the available light efficiently, helping them remain visible to each other while blending perfectly with the ethereal glow of their environment. Many have large eyes, adapted to gather as much of the available light as possible. They move through this blue-green space with an easy grace, perfectly at home in what seems to us like an alien environment. Some fish at these depths have evolved to actually enhance the available light through a process called bioluminescence, the ability to create their own light through chemical reactions within their bodies. But these biological lights are typically blue or blue-green as well, matching the color of the filtered sunlight that reaches these depths. It's as if the entire ecosystem has reached a consensus about which colors work best in this environment. As we approach the 500-foot mark, we begin to notice that the light, while still present and beautiful, is noticeably dimmer than what we experienced in the shallower waters. This isn't a sudden change. We've been gradually adjusting to decreasing light levels throughout our descent. But at some point, we become conscious that we're entering a different realm, a place where light is becoming precious, where each remaining photon represents a small victory in the long journey from the surface. The blue-green glow around us is still sufficient for vision, still bright enough to appreciate the beauty of this underwater world, but there's a sense that we're approaching the limits of where surface sunlight can effectively penetrate. We're entering what marine biologists call the twilight zone, the region where day and night begin to lose their meaning, where the rhythm of surface lighting gives way to the constant, gentle glow of filtered sunshine. At 600 feet deep, the transformation becomes even more apparent. The light around us is now a deep, rich blue-green, like the color of a perfect gemstone held up to a window. It's still beautiful, still sufficient for us to see and appreciate our surroundings. But it's clear that we're in a place where every photon has traveled an extraordinary distance, has survived countless encounters with water molecules, has been filtered and refined until only the most persistent wavelengths remain. Think about the journey each of these remaining photons has made. They began their existence in the nuclear fires of the sun, created in fusion reactions that convert hydrogen into helium and release enormous amounts of energy. They traveled for 8.5 minutes through the vacuum of space, covering 93 million miles at the speed of light. They passed through Earth's atmosphere, scattering off air molecules and dust particles. They entered the ocean and began their slow descent through layer after layer of water, each foot of depth requiring countless molecular encounters. By the time a photon reaches us at 600 feet, it has survived a gauntlet of absorption opportunities. Countless water molecules have had the chance to absorb its energy, to transform its electromagnetic radiation into heat. The fact that it's still here, still carrying its message of light from the sun, represents an almost miraculous persistence. These are the photons that have won the lottery, the ones that have made it through the filters and reached this deep blue-green realm. And yet, even as we appreciate the remarkable journey of these surviving photons, we can sense that their travels are far from over. Below us, the ocean continues for thousands of feet more, each additional layer adding its own filtering effect, its own opportunities for absorption. The light around us, beautiful as it is fighting a losing battle against the patient, persistent embrace of countless water molecules. At 700 feet, the blue-green light takes on an even deeper, richer quality. It's like being surrounded by liquid sapphire, a glow so pure and intense that it seems almost mystical. But this intensity comes from concentration rather than brightness. We're seeing the distilled essence of sunlight, the most persistent wavelengths that have survived the long filtering process. The few fish we encounter at this depth move like ghosts through the blue-green glow, their movements deliberate and efficient. Many have enlarged eyes, evolutionary adaptations that allow them to gather as much of the available light as possible. Some are beginning to supplement the filtered sunlight with their own bioluminescent capabilities, creating tiny points of blue-green light that appear and disappear like stars in a liquid night sky. As we descend past 800 feet, we begin to understand that we're witnessing one of nature's most beautiful demonstrations of persistence and transformation. The light around us represents the triumph of the most resilient photons, the ones that have navigated the complex obstacle course of the ocean's upper layers and reached these depths still carrying their original message from the sun. But we can also sense that this triumph is temporary. The water below us continues for thousands of feet more, and each additional layer will claim its share of these remaining photons. The beautiful blue-green glow that surrounds us is not a permanent feature of these depths, but rather a moment in the ongoing process of light's transformation into darkness. At 900 feet, the light around us is taken on an almost electric quality, so intensely blue-green that it seems to vibrate with energy. This is the distilled essence of sunlight, filtered through nearly 1,000 feet of seawater, concentrated into the wavelengths that interact least readily with water molecules. It's breathtakingly beautiful, but also somehow poignant. We're witnessing the last gasps of surface sunshine, the final stage before the transition to eternal darkness. The water at this depth feels different too, not just in its visual character, but in its very essence. The pressure here is significantly greater than at the surface, nearly 30 times normal atmospheric pressure. This pressure affects how light behaves, subtly altering the interactions between photons and water molecules, contributing to the unique character of deep water illumination. As we approach the 1,000-foot mark, we find ourselves suspended in what can only be described as liquid light. The blue-green glow around us is so pure, so concentrated, that it seems less like illumination and more like a luminous medium, as if we're floating inside a giant blue-green crystal. It's an otherworldly experience, beautiful and strange and deeply peaceful. But even as we marvel at this extraordinary environment, we can sense the inevitability of what lies ahead. Below us, the ocean continues its patient work of light absorption, each layer claiming its share of photons, each foot of depth reducing the number of survivors from the original surface illumination. We're approaching the boundary between the world of light and the realm of eternal darkness, the place where even the most persistent photons finally surrender their energy to the loving embrace of water molecules. This is where our journey takes on its most profound meaning. We're witnessing not just the physics of light absorption, but a deeper truth about transformation and acceptance. The ocean teaches us that even the most powerful forces, the light of our sun, can be gradually, gently, lovingly absorbed into something larger than themselves. The darkness that awaits us in the deeper layers isn't a failure of light, but light's own peaceful transformation into a different form of energy. As we prepare to descend even deeper into layers where no surface light has ever penetrated, we carry with us the memory of this beautiful blue-green glow, this distilled essence of sunshine that has traveled so far and overcome so many obstacles to reach these depths. In the chapters ahead, we'll explore what happens when even these most persistent photons finally surrender their light and discover the different kind of beauty that exists in the ocean's deepest, darkest realms. Here we are, suspended in this ethereal blue-green glow at nearly 1,000 feet beneath the surface, witnessing something that few humans have ever experienced firsthand. Around us, the ocean continues its ancient, patient work of transforming light into warmth. But now we're going to slow down our descent and really observe this process in detail. We're going to watch the dance of absorption, the gentle choreography between photons and water molecules that creates one of nature's most beautiful demonstrations of gradual transformation. Take a moment to really appreciate where we are. Above us, nearly a quarter mile of water stretches upward toward the distant surface, each foot of that column contributing to the filtering process that has created this extraordinary blue-green environment. Below us, the ocean continues for thousands of feet more, each layer waiting to add its own contribution to the ongoing absorption of light. We're floating in a space that represents the meeting point between the world of surface illumination and the realm of eternal darkness. The light around us at this depth has a quality unlike anything you might experience on land. It's not the bright, directional light of sunshine streaming through a window, nor is it the warm, flickering light of a candle or fireplace. Instead, it's a cool, omnidirectional glow that seems to emanate from the water itself, as if we're suspended inside a giant blue-green lantern. This quality comes from the countless scattering events that each photon has experienced during its journey downward, bouncing gently off water molecules and particles until the light comes from every direction at once. To understand what's happening around us, let's focus on a single photon for a moment. Imagine one blue-green photon, part of the filtered sunlight that surrounds us, as it continues its journey deeper into the ocean. This photon has already survived nearly 1,000 feet of potential absorption opportunities. It began as part of the white light streaming down from the sun, but its red and orange companions were absorbed long ago, their energy transformed into the subtle warmth that characterizes the ocean's upper layers. Our blue-green photon moves through the water at the speed of light, but its path isn't straight. Like a butterfly following an invisible, three-dimensional maze, it zigzags gently through the water as it encounters molecules and particles. Sometimes it passes between them unchanged. Sometimes it bounces off at a slight angle, its direction altered, but its energy intact. And sometimes, just sometimes, it encounters a water molecule that's oriented just right, vibrating at just the right frequency to absorb its energy completely. When absorption happens, it's remarkably gentle. There's no violence, no dramatic collision. Instead, the photon simply transfers its energy to the water molecule, causing it to vibrate slightly faster, to move with a tiny bit more energy than it had before. The photon disappears, its journey complete, but its energy lives on as a minute increase in the water's temperature. It's like a relay race where the baton is heat instead of a physical object, passed from light to matter in the most graceful exchange imaginable. This process of absorption follows what scientists call an exponential decay curve, though that mathematical term doesn't quite capture the gentle, organic nature of what's actually happening. Think of it instead like autumn leaves falling from a tree. At first, most of the leaves remain on the branches, with just a few drifting down. But as time passes, more and more leaves let go, until eventually the tree is bare. The rate of falling increases as time goes on, but each individual leaf falls gently, naturally, when its moment arrives. The same thing happens with photons in seawater. At shallow depths, most of the light continues downward, with just a small percentage being absorbed. But as the depth increases, the percentage of absorbed light grows larger, following a predictable mathematical relationship that oceanographers call the Beer-Lambert law. It's a beautifully elegant equation that describes how light intensity decreases exponentially with depth, but behind that mathematical precision lies this remarkably gentle process of molecular interaction. As we float here in our blue-green sanctuary, we can actually observe this process in action if we pay close attention. The light around us isn't perfectly uniform. If you look carefully, you might notice subtle variations in brightness, tiny fluctuations that come and go like gentle waves. These variations reflect the random nature of absorption events happening all around us. In some regions, a few more photons happen to be absorbed, creating a slightly dimmer area. In others, fewer absorptions occur, leaving the light slightly brighter. But these variations are incredibly subtle, like the difference between one shade of blue-green and a very slightly different shade of blue-green. The overall effect is still one of remarkable uniformity of light that seems to come from everywhere and nowhere at once. It's this uniformity that creates the otherworldly quality of deep water illumination, the sense that we're floating in liquid light rather than simply being illuminated by it. The water molecules responsible for this absorption are constantly in motion, vibrating and rotating in the three-dimensional dance that characterizes all matter at the molecular level. At the temperature of deep seawater, cool but not freezing, these molecules move with just the right amount of energy to interact effectively with certain wavelengths of light. They're like microscopic tuning forks, each one resonating at specific frequencies, ready to accept the energy of photons that match their vibrational characteristics. Interestingly, the absorption of light by water isn't perfectly random. Different parts of the water molecule, the hydrogen atoms, the oxygen atom, the bonds between them, have slightly different preferences for which wavelengths they'll absorb. This selectivity is what creates the beautiful progression of color changes we've observed during our descent. The reds and oranges were absorbed preferentially by certain molecular vibrations, while the blues and greens have been allowed to pass through more easily. But even among the blues and greens, there are subtle preferences. The deeper we go, the more we notice that the light is shifting toward a very specific shade of blue-green, the wavelength that water molecules absorb least readily. It's as if the ocean is naturally selecting for this particular color, allowing it to penetrate deeper than any other part of the visible spectrum. This wavelength, around 480 nanometers on the electromagnetic spectrum, represents the sweet spot where water's absorption is at its minimum. As we descend a bit deeper, perhaps to 1,200 feet, we can observe this selection process continuing. The light around us becomes even more concentrated in this optimal blue-green wavelength, creating an illumination that's increasingly pure and intense. It's like listening to a symphony where all the instruments gradually fade away except for one perfect note, played with increasing clarity and precision as the other sounds disappear. At this depth, the pressure around us is increased to nearly 40 times normal atmospheric pressure, and this pressure affects the absorption process in subtle but important ways. Under high pressure, water molecules are packed more closely together, and their vibrational characteristics change slightly. This doesn't dramatically alter the absorption of light, but it does fine-tune the process, creating slight variations in how different wavelengths are absorbed compared to the surface. The marine life at these depths has evolved to take advantage of this increasingly pure blue-green light. Many deep-sea fish have eyes that are specifically tuned to this wavelength, with visual pigments that are most sensitive to the exact color that penetrates deepest into the ocean. It's a beautiful example of how life adapts to its environment, fine-tuning its sensory apparatus to extract the maximum information from the available light. Some creatures at this depth have gone even further, developing bioluminescent capabilities that produce light at exactly the same wavelength as the filtered sunlight. Their biological lights blend seamlessly with the ambient illumination, creating a kind of camouflage that makes them nearly invisible to predators or prey. It's as if they've learned to speak the ocean's own language of light, communicating in the same blue-green vocabulary that nature has selected for these depths. As we continue our gentle descent toward 1,500 feet, we begin to notice that the absorption process is accelerating. Not because individual absorption events are happening faster, but because there are fewer and fewer photons remaining to be absorbed. It's like the final notes of a musical piece fading away. Each note is just as clear as before, but there are fewer of them, creating a sense of approaching silence. The light around us at this depth has taken on an almost crystalline quality, so pure and concentrated that it seems more like a luminous medium than mere illumination. We're witnessing the distilled essence of sunlight, refined through 1,500 feet of molecular filtering into something that barely resembles the white light that began this journey at the surface. It's breathtakingly beautiful, but also somehow poignant. We're seeing the last traces of solar energy before it completes its transformation into heat. At 1,800 feet, the absorption process becomes even more apparent. The light around us, while still present and still beautiful, is noticeably dimmer than what we experience just a few hundred feet above. Each remaining photon represents a small miracle of persistence, having survived countless opportunities for absorption during its long journey from the surface. These are the champion photons, the ones that have navigated the molecular obstacle course with the skill of master athletes. But even these champions are fighting a losing battle. Below us, thousands of feet of water remain, each layer ready to claim its share of the remaining light. The mathematical precision of exponential decay means that with each additional foot of depth, a predictable percentage of the remaining photons will be absorbed. It's a gentle but inexorable process, as reliable as the tide, as patient as geology. At 2,000 feet deep, we find ourselves in what can only be described as the twilight of sunlight. The blue-green glow around us is still sufficient for vision, still bright enough to appreciate the ethereal beauty of this deep water environment. But there's an unmistakable sense that we're approaching the limits of where surface illumination can effectively penetrate. We're witnessing the final act in the drama of light absorption, the last scene before the curtain falls on solar illumination. The few remaining photons around us carry with them the memory of their incredible journey. They've traveled 93 million miles through space, passed through Earth's atmosphere, and descended through 2,000 feet of seawater, surviving countless opportunities for absorption along the way. Each one represents a tiny triumph of persistence over probability, a demonstration that even in a world governed by statistical laws, individual particles can sometimes beat the odds. But statistics always win in the end, and we can sense that even these most persistent photons are approaching the end of their journey. The water below us continues for thousands of feet more, and the mathematical certainty of exponential absorption means that each additional layer will claim its predictable share of the remaining light. We're witnessing not just the physics of light absorption, but a deeper truth about persistence and surrender, about the way even the most determined travelers eventually find their destination and rest. As we prepare to descend into even deeper waters, we carry with us a profound appreciation for this dance of absorption we've been privileged to witness. The gentle, patient process by which water molecules accept the energy of photons and transform light into warmth represents one of nature's most beautiful demonstrations of transformation. It's a process that's been going on for billions of years, since the first oceans formed on Earth, refined through countless eons into the elegant molecular choreography we've observed. The beauty of this process lies not just in its scientific precision, but in its fundamental gentleness. There's no violence here, no struggle or conflict. Instead, there's a kind of cosmic cooperation, a willingness of light to be transformed and of water to accept that transformation. Each absorption event represents a moment of perfect harmony between electromagnetic energy and matter, a tiny demonstration of the interconnectedness that underlies all natural processes. As we float here at the boundary between the world of filtered sunlight and the realm of eternal darkness, we can feel ourselves becoming part of this ancient process. The water around us supports us gently, just as it supports the photons in their journey toward absorption. We're not separate observers of this molecular dance, but participants in a larger pattern of energy exchange that characterizes all life in the ocean. Soon, we'll descend into depths where no surface light has ever penetrated, where the dance of absorption has been completed and all solar photons have surrendered their energy to the patient embrace of water molecules. But we'll carry with us the memory of this beautiful blue-green glow, this distilled essence of sunshine that has shown us how even the most persistent energy eventually finds peace and transformation. Here we are, suspended at the threshold between two worlds. Above us lies the realm we've been exploring, where filtered sunlight creates that ethereal blue-green glow we've come to appreciate so deeply. Below us stretches the beginning of something entirely different, the twilight zone of the ocean, where day and night lose their surface meanings and light becomes increasingly precious with every foot of descent. At 2,000 feet beneath the surface, we find ourselves in a place that exists nowhere else on Earth. The light around us is so refined, so concentrated into that perfect wavelength of blue-green, that it seems almost supernatural. But we can sense that we're approaching a fundamental transition, the place where even this most persistent sunlight will finally surrender to the patient embrace of the deep ocean. Let's pause here for a moment and truly appreciate the magnitude of what we're witnessing. Every photon that reaches this depth has completed an extraordinary journey. Think about the odds a single particle of light has overcome to arrive here with us. Starting from the nuclear fusion reactions in the sun's core, traveling through 93 million miles of space, passing through Earth's atmosphere, and then navigating 2,000 feet of increasingly dense water, surviving countless opportunities for absorption along the way. The mathematics of this survival are quite remarkable. Scientists have calculated that only about 1% of the surface sunlight reaches these depths, and that 1% is concentrated almost entirely in the blue-green wavelengths we're experiencing now. We're surrounded by the champions of the light world, the photons that have beaten astronomical odds to reach this deep sanctuary. But even champions grow tired, and we can sense that these persistent travelers are approaching the end of their journey. The absorption process that we observed so gently in the layers above continues here with the same patient persistence. But now it's working on an increasingly small population of photons. It's like watching the final runners in a marathon. There are fewer of them, but each one represents an extraordinary achievement of endurance. As we begin our descent from 2,000 feet toward the deeper twilight layers, the character of the light around us starts to change in subtle but profound ways. The blue-green glow that has surrounded us becomes more concentrated, more intense, but also noticeably dimmer. It's as if we're watching a beautiful fire burn down to its final, most essential flames. The light is purer than ever, but there's less of it with each passing moment. At 2,500 feet, we enter what marine biologists formally call the dysphotic zone, though that clinical term hardly captures the ethereal beauty of this environment. Dysphotic means poorly lit, but there's nothing poor about the illumination around us. Instead, it's light at its most refined, most distilled, like the difference between a bright neon sign and a single, perfect candle flame. Both provide illumination, but they create entirely different atmospheres, entirely different experiences. The water around us at this depth feels different in ways that go beyond just the visual. The pressure here is nearly 80 times greater than at sea level, enough to compress air to a fraction of its surface volume. This pressure affects everything: how sound travels, how gases dissolve, how molecules interact with each other and with light. The water feels denser, more substantial, as if we're floating through liquid metal rather than ordinary seawater. But this density doesn't make the environment oppressive. Instead, it creates a sense of being held, supported, embraced by something solid and reliable. The water around us is no longer the thin, almost invisible medium we might experience while swimming at the surface. Here it has presence, weight, substance. We can feel ourselves suspended in something that has real character, real personality. The marine life at this depth has adapted to this twilight environment in fascinating ways. Many fish have developed enlarged eyes, sometimes grotesquely large compared to their body size, designed to capture every available photon of the precious blue-green light. These eyes work like biological telescopes, gathering light with remarkable efficiency and focusing it onto highly sensitive retinas that can detect illumination levels thousands of times dimmer than what human eyes require. Some creatures have taken a different approach entirely, developing their own light sources through bioluminescence. But interestingly, these biological lights are typically the same blue-green color as the filtered sunlight around us. It's as if the entire deep-sea ecosystem has reached a consensus about which wavelength of light works best in this environment. The creatures here don't fight against the ocean's preference for blue-green light. They embrace it, incorporating it into their own biology. As we descend toward 3,000 feet, we begin to notice something remarkable happening to our perception of time. Without the familiar rhythm of day and night, without the changing quality of surface sunlight to mark the passage of hours, time seems to slow down, to become more fluid. The eternal blue-green twilight creates a sense of existing outside normal temporal flow, as if we've entered a realm where minutes and hours are measured differently. This timeless quality is one of the most striking characteristics of the deep ocean's twilight zone. On the surface, we're accustomed to light that changes constantly. Bright midday sun, golden afternoon rays, the warm colors of sunset, the gradual transition to nighttime darkness. But here, the light is constant, unchanging, eternal. It creates an environment that feels removed from the normal cycles that govern surface life. The consistency of this twilight illumination has profound effects on the creatures that live here. Many deep-sea fish have lost the circadian rhythms that regulate the behavior of surface animals. Without day and night to provide temporal cues, they've developed different patterns of activity, different ways of organizing their lives. Some follow the vertical migration patterns of their prey. Others respond to seasonal changes in food availability that filter down from the surface layers. But few pay attention to the 24-hour cycle that dominates surface existence. At 3,500 feet, we find ourselves in light so dim that it's approaching the limits of what most surface creatures would consider illumination at all. But our eyes have been gradually adjusting during our long descent, and we can still see the beautiful blue-green glow that surrounds us. It's like the difference between reading by bright sunlight and reading by moonlight. Both are possible, but they require different kinds of visual adaptation. The light at this depth has an almost mystical quality, so pure and concentrated that it seems to vibrate with energy. We're witnessing the absolute essence of sunlight, refined through 3,500 feet of molecular filtering into something that barely resembles the white light that began this journey at the surface. Every photon around us represents the pinnacle of optical persistence, having survived odds that would make lottery winners feel common. But we can sense that even this essence is temporary. The absorption process continues below us, patient and inexorable, ready to claim these final champions of surface illumination. The water beneath our feet stretches for thousands more feet, each layer adding its contribution to the ongoing transformation of light into heat. We're witnessing the final act of a drama that began 93 million miles away in the nuclear fires of the sun. As we approach 4,000 feet, something profound happens to the light around us. It doesn't disappear suddenly. That's not how the ocean works. Instead, it begins to fade with the gentle inevitability of twilight on a summer evening. The blue-green glow that has been our constant companion starts to dim, not through any dramatic change, but through the simple mathematics of exponential absorption. At this depth, we're receiving less than 0.1% of the surface sunlight, and that tiny fraction is concentrated almost entirely in the narrow band of blue-green wavelengths that water absorbs least readily. We're like visitors to a museum after closing time, exploring exhibits by the light of emergency illumination. There's enough light to see, but just barely, and we know that soon even this minimal illumination will be reduced further. The creatures at 4,000 feet live in this perpetual near darkness, but they've adapted so completely to their environment that they thrive here. Many have developed other senses to replace vision. Enhanced lateral line systems that can detect the slightest water movements, chemical sensors that can track prey or predators by taste and smell, electrical sensors that can detect the bioelectric fields generated by other living creatures. But perhaps most remarkably, many deep-sea creatures have become living light sources themselves. Bioluminescence becomes increasingly common as we descend into these darker waters, as if life itself is taking over the job of illumination as the sun's contribution diminishes. These biological lights serve many purposes: communication, camouflage, prey attraction, predator deterrence. But they all contribute to creating a kind of secondary lighting system in the ocean's deeper layers. At 4,500 feet, we find ourselves in what can only be described as the deep twilight. The blue-green glow around us is now so dim that it's more of a hint than actual illumination, like the first light of dawn when it's still too dark to read, but you can sense that morning is approaching. Except here, we're moving away from morning, deeper into an oceanic night that will never end. The water around us feels incredibly dense now, compressed by the enormous weight of the column above us. The pressure at this depth is over 140 times greater than at sea level, enough to crush most surface vessels like aluminum cans. But life continues here, adapted to this high-pressure environment, thriving in conditions that would be instantly fatal to surface creatures. As we descend past 5,000 feet, we cross an invisible but profound boundary. Here, The last traces of direct sunlight finally surrender to the patient embrace of the deep ocean. The photons that have traveled so far, survived so much, finally encounter their destined water molecules and transfer their energy in that gentle, graceful exchange we've been observing throughout our journey. This isn't a sudden transition. There's no wall of darkness that we pass through. Instead, it's like watching the last embers of a fire fade away, a gradual dimming that eventually reaches a point where we can no longer distinguish between the faintest possible light and complete darkness. The blue-green glow that has been our companion for so long finally fades to black, not through any dramatic event, but through the simple exhaustion of every last surface photon. But darkness here doesn't mean emptiness. As our eyes adjust to the absence of sunlight, we begin to notice something magical. The ocean's own lights beginning to appear. Tiny sparkles of bioluminescence start to become visible, like stars emerging in the evening sky as daylight fades. These are the lights created by living creatures, the ocean's own replacement for the sunlight that can no longer reach these depths. The transition from sunlight to bioluminescence represents one of the most beautiful handoffs in nature. As the sun's contribution to deep-sea illumination finally reaches zero, life takes over the job of creating light. It's as if the ocean has its own backup lighting system, ready to activate the moment the primary source fails. The continuity is seamless, the transition as smooth as a well-choreographed dance. At 6,000 feet deep, we find ourselves in true darkness punctuated by living light. The complete absence of sunlight creates an environment unlike anywhere else on Earth, a place where the only illumination comes from the creatures themselves. It's like floating through a three-dimensional constellation, where points of blue and green light appear and disappear in the gentle rhythms of deep-sea life. This bioluminescent display is breathtakingly beautiful, but it also represents something profound about life's adaptability. Faced with the complete absence of external light, creatures have evolved the ability to create their own illumination. They become living stars in the ocean's liquid night sky, each one contributing to a light show that rivals anything visible from the surface. As we float here in this bioluminescent wonderland, we can reflect on the complete journey we've taken. We began in the bright, warm surface waters where sunlight painted everything in the full spectrum of colors. We descended through layers where that light was gradually filtered and refined, watching reds and oranges disappear first, then yellows, then finally all but the most persistent blue-green wavelengths. We observed the patient, gentle process by which water molecules absorbed photon after photon, transforming electromagnetic energy into heat in countless tiny exchanges. We witnessed the mathematical precision of exponential decay playing out in real time, as the population of surviving photons diminished predictably with each additional foot of depth. And finally, we've arrived at the boundary between the sunlit world above and the bioluminescent realm below, the place where the sun's influence ends and life's own creativity begins. We've completed the transition from external illumination to internal light generation, from the physics of absorption to the biology of bioluminescence. This transition represents more than just a change in lighting sources. It symbolizes something deeper about the relationship between life and energy, about the way living creatures can adapt to even the most challenging environments. The deep ocean's twilight zone isn't a place where life struggles against the absence of light. It's a place where life has learned to create its own light, to illuminate its own world through the magic of biochemistry. As we prepare to explore even deeper layers, where bioluminescence becomes the primary source of illumination and the memory of sunlight fades into history, we carry with us a profound appreciation for this twilight realm. We've witnessed the gentle completion of light's transformation, the place where photons that began their journey in the nuclear fires of the sun finally find their peaceful rest in the molecular embrace of seawater. The beauty of this process lies in its fundamental gentleness, its patient inevitability, its demonstration that even the most powerful forces eventually find their place of rest. The ocean's twilight zone teaches us about transformation, about the way energy changes form but never disappears, about the seamless transition from one kind of beauty to another. Soon, we'll descend into the true deep sea, where no trace of surface light has ever penetrated and life creates all its own illumination. But we'll carry with us the memory of this twilight realm, this boundary zone where sunlight makes its gentle surrender to the patient darkness of the deep ocean. As we continue our peaceful descent beyond the twilight zone, having witnessed the final surrender of surface sunlight to the ocean's patient embrace, we enter a realm where an entirely different kind of optical phenomenon becomes the star of our story. We're now in waters where direct sunlight has never penetrated, but that doesn't mean our journey with light is over. Instead, we're about to discover how the ocean creates its own subtle illumination through one of nature's most elegant processes, the scattering symphony. Here, suspended in what marine scientists call the bathypelagic zone, we find ourselves in true darkness punctuated by the living lights of bioluminescent creatures. But even in this darkness, there's a story of light that continues to unfold around us. It's not the story of photons arriving directly from the sun, but rather the tale of how even the faintest traces of illumination can be transformed, redirected, and multiplied through the gentle process of scattering. To understand what's happening around us now, we need to think about light in a slightly different way. Throughout our descent, we focused primarily on absorption, the process by which water molecules accept photon energy and transform into heat. But absorption isn't the only thing that happens when light encounters matter. Sometimes, instead of being absorbed, a photon bounces off a molecule or particle, changing direction but retaining its energy. This bouncing is called scattering, and it plays a crucial role in how illumination behaves in the deep ocean. Even here, thousands of feet below the last traces of direct sunlight, scattering continues to work its gentle magic. The few bioluminescent photons created by living creatures don't simply travel in straight lines and disappear into the darkness. Instead, they encounter the same water molecules and suspended particles that scattered the sunlight above, and they bounce and ricochet in the same gentle ballet we observed in the brighter layers. Imagine a single photon of blue-green light, created by a small deep-sea creature perhaps 100 feet away from us. This photon begins its journey in a specific direction, carrying its tiny packet of energy through the dark water. But almost immediately, it encounters a water molecule and bounces off at a slight angle. Now it's traveling in a new direction, but with the same energy it started with. A few feet later, it encounters another molecule and bounces again. Then it hits a small particle of organic matter drifting down from the surface layers above, and once again changes direction. Each encounter redirects the photon's path, but doesn't diminish its brightness. It's like watching a microscopic game of three-dimensional pinball, where the ball never loses energy, but constantly changes course. This scattering process has a remarkable effect on bioluminescent light in the deep ocean. Instead of the sharp, directional beams you might expect from biological light sources, the illumination becomes soft, diffused, omnidirectional. A fish that creates a point of blue-green light doesn't just illuminate the space directly in front of it. The scattering process spreads that light in all directions, creating a gentle glow that fills the surrounding water. The mathematics of scattering follow what's called Rayleigh scattering, the same process that makes Earth's sky blue and creates the red colors of sunrise and sunset. In the deep ocean, this process works on the sparse bioluminescent light to create subtle but important effects. The blue-green wavelengths that most deep-sea creatures use for their bioluminescence are scattered relatively efficiently by water molecules, which means that even a small amount of biological light can create a surprisingly widespread illumination. But scattering in the deep ocean isn't just about individual water molecules. The deep sea is filled with tiny particles, bits of organic matter that have drifted down from the surface, microscopic organisms, tiny fragments of calcium carbonate from shellfish, particles of clay that have been carried by deep currents from distant shores. Each of these particles contributes to the scattering process, adding its own contribution to the gentle redistribution of light. This creates what scientists call the marine snow. Not the precipitation we might know from winter weather, but a slow, constant drift of tiny particles falling through the water column like microscopic snowflakes. These particles are excellent scatterers of light, much more efficient than water molecules alone. When bioluminescent light encounters this marine snow, it creates tiny sparkles and glints like sunlight on fresh snow. Except here the sunlight is replaced by the gentle glow of living creatures. As we float here in this environment, 6,000 feet below the surface, we can observe the scattering symphony in action. When a deep-sea jellyfish creates a pulse of bioluminescent light, that light doesn't simply illuminate the jellyfish itself and then disappear into the darkness. Instead, it spreads outward in all directions, bouncing off water molecules and particles, creating a sphere of gentle illumination that can be detected hundreds of feet away. This scattered light serves many purposes in the deep-sea ecosystem. For predators, it can reveal the presence of prey that might otherwise remain invisible in the darkness. For prey species, the scattering can help them detect approaching danger. For creatures seeking mates, the widespread distribution of scattered bioluminescent signals increases the chances that their communications will be received across the vast distances of the deep ocean. The process is beautifully democratic. Every particle, every molecule, every tiny fragment of matter in the water contributes to the scattering symphony. There's no central conductor, no master plan, just billions of individual scattering events that combine to create a complex, ever-changing pattern of light distribution. It's like a three-dimensional light show where every element of the environment participates in creating the final effect. One of the most remarkable aspects of deep-sea scattering is how it amplifies the effectiveness of bioluminescence. A creature that creates just a tiny amount of biological light can, through the scattering process, illuminate a much larger volume of water than would be possible if the light traveled only in straight lines. It's as if the ocean itself becomes a partner in the creature's lighting system, helping to distribute the illumination as widely and effectively as possible. The particles that contribute to scattering in the deep ocean have their own fascinating stories. Some are the remains of microscopic plants that lived in the sunlit surface waters and have been slowly sinking for weeks or months, their cellular structures gradually breaking down as they fall. Others are the waste products of marine animals, tiny pellets that carry nutrients from the upper ocean layers down to the deep sea floor. Some particles are mineral in origin, tiny crystals of calcium carbonate that form in the surface waters when certain organisms build their shells, or particles of clay that have been transported thousands of miles by ocean currents before settling into the depths. Each type of particle has its own scattering characteristics, its own way of interacting with light, contributing to the complex optical environment of the deep sea. The temperature and pressure at these depths also affect the scattering process. In the near-freezing temperatures and crushing pressures of the deep ocean, water molecules behave slightly differently than they do at the surface. They're packed more closely together. Their vibrational characteristics are altered, and their interaction with light takes on subtle new characteristics. These changes don't dramatically alter the scattering process, but they do fine-tune it, creating the specific optical environment that deep-sea creatures have evolved to exploit. As we continue our descent toward 7,000 feet, we can observe how the scattering symphony creates layers of illumination that have nothing to do with the original distribution of light sources. A group of bioluminescent organisms in one area can, through scattering, create a gentle glow that extends far beyond their immediate vicinity. This scattered light can then encounter other scattering particles and be redirected again, creating complex patterns of illumination that shift and change as currents move particles through the water. The result is an environment where light behaves in ways that would seem magical if we encountered them on land. Illumination appears to come from everywhere and nowhere, creating a sense of existing within luminous water rather than simply being illuminated by external sources. It's like floating inside a very gentle, very slow lightning storm, where the flashes of bioluminescent light are spread and softened by the scattering process until they create an otherworldly glow. This scattered illumination has profound effects on how deep-sea creatures perceive their environment. Unlike surface animals, who are accustomed to directional lighting that creates shadows and highlights, deep-sea creatures live in a world of diffused, omnidirectional illumination. Their visual systems have evolved to process this scattered light efficiently, to extract maximum information from the gentle, widespread glow that characterizes their environment. Many deep-sea fish have developed eyes that are specifically designed to detect scattered light. These eyes often have large pupils and highly sensitive retinas, but they also have specialized optical structures that help them process diffuse illumination. Some species have developed eyes that can detect polarized light, taking advantage of the fact that scattered light often becomes polarized as it bounces off particles and molecules. The scattering symphony also plays a crucial role in the deep ocean's food webs. Many deep-sea creatures rely on detecting scattered bioluminescent light to locate their prey. A small fish might create a brief flash of light when startled, and that flash, scattered by the surrounding water and particles, can be detected by predators from surprisingly large distances. The scattering process effectively increases the communication range of bioluminescent signals, making the deep ocean a more connected environment than it might otherwise be. At 8,000 feet deep, we find ourselves in an environment where the scattering symphony has become one of the dominant features of the optical landscape. The pressure here is nearly 250 times greater than at sea level, enough to compress air to a tiny fraction of its surface volume. This pressure affects the density of water and the behavior of suspended particles, subtly influencing how scattering occurs. The marine snow at this depth includes particles that have been falling for months, slowly drifting downward from the productive surface waters far above. Some of these particles are aggregates, clusters of smaller particles that have stuck together during their long journey, creating larger scattering centers that interact with light in complex ways. These aggregates can create particularly beautiful scattering effects, spreading bioluminescent light in intricate patterns that change as the particles slowly rotate and tumble through the water. As we approach 9,000 feet, we begin to notice that the scattering symphony has created something remarkable: layers of enhanced illumination that persist for hours or even days. When large numbers of bioluminescent organisms congregate in particular areas, their combined light output, spread and amplified by scattering, can create zones of persistent low-level illumination. These zones don't depend on continuous light production. Instead, they represent the accumulated effect of countless scattering events building up a background glow that outlasts the original light sources. This phenomenon creates what some marine biologists call light memory in the deep ocean, areas where the scattering process has captured and redistributed enough bioluminescent light to create a lingering glow. It's as if the water itself has learned to hold on to light, to store it temporarily in the complex dance of scattering particles before eventually allowing it to fade into the surrounding darkness. The creatures that live at these depths have evolved to take advantage of this light memory. Some species time their activities to coincide with periods of enhanced scattered illumination, using the background glow to hunt more effectively or to navigate through their three-dimensional environment. Others have learned to create their own enhanced scattering zones by coordinating their bioluminescent displays, effectively collaborating to increase the total amount of available light. At 10,000 feet deep, we find ourselves in an environment where the scattering symphony has reached its full complexity. Here, the interaction between bioluminescent light sources, suspended particles, water molecules, and the physical properties of high-pressure seawater creates an optical environment that exists nowhere else on Earth. The illumination here is entirely created and shaped by life itself, distributed and amplified by the physical properties of the medium in which that life exists. The beauty of the scattering symphony lies in its fundamental cooperation. Every element of the environment, living and non-living, contributes to the creation and distribution of light. Bioluminescent creatures provide the initial illumination, water molecules redirect and spread that light, suspended particles add their own scattering effects, and the physical properties of deep seawater fine-tuned the entire process. This cooperation creates an environment that's far more illuminated than it would be if light simply traveled in straight lines from its sources. The scattering process multiplies the effectiveness of every bioluminescent photon, ensuring that the sparse light sources of the deep ocean can create a more connected, more navigable environment for the creatures that call these depths home. As we float here in this gently glowing darkness, 10,000 feet below the surface, we can appreciate the elegant efficiency of the scattering symphony. It's a process that requires no energy input beyond the initial bioluminescent light production, yet it dramatically enhances the optical environment of the deep ocean. It's physics and biology working together in perfect harmony, creating beauty and functionality through the simple process of light bouncing off matter. The scattering symphony teaches us something profound about cooperation and amplification. Just as individual voices can combine to create a chorus more beautiful than any single singer, individual scattering events combine to create an optical environment more rich and complex than any individual light source could produce alone. It's a demonstration of how simple physical processes, repeated countless times, can create emergent properties that transform an entire ecosystem. As we prepare to descend even deeper into layers where the scattering symphony continues, but takes on new characteristics in the crushing pressures and near-freezing temperatures of the abyssal depths, we carry with us an appreciation for this gentle process of light redistribution. We've seen how even in the deepest darkness, light finds a way to spread, to connect, to create illumination where none existed before. The scattering symphony reminds us that darkness and light are not simply opposite states, but rather different points on a spectrum of illumination that includes countless subtle gradations. In the deep ocean, these gradations are created not by the sun, but by life itself, working in partnership with the physical properties of seawater to create one of nature's most beautiful and efficient lighting systems. As we continue our peaceful journey deeper into the ocean's embrace, having witnessed the scattering symphony transform sparse bioluminescent light into gentle, widespread illumination, we arrive at a place of profound significance in our exploration of why the deep sea remains forever dark. Here, suspended 12,000 feet beneath the surface, we reach the final boundary where even the most persistent wavelength of visible light, that beautiful blue-green that has accompanied us for so long, finally surrenders to the patient darkness. This surrender doesn't happen suddenly, like flipping a switch from light to dark. Instead, it unfolds with the same gentle inevitability we've observed throughout our journey, a gradual transition that speaks to the ocean's fundamental character of patient, persistent transformation. We're witnessing the completion of a process that began at the surface, where white sunlight first encountered seawater and began its long journey toward this final destination. To understand what makes this depth so special, we need to return to the physics of light absorption that we've been observing throughout our descent. Remember how different colors of light were absorbed at different rates as we traveled deeper? The warm reds and oranges disappeared first, absorbed readily by water molecules in the upper layers. The yellows followed, then the cooler colors, until only the blue-green wavelengths remained to accompany us into the twilight zone. But even blue-green light, persistent as it has been, is not immune to absorption. The same gentle process that claimed all the other colors continues to work on these final wavelengths, molecule by molecule, photon by photon, with the same patient persistence we've observed throughout our journey. At 12,000 feet, we've reached the mathematical endpoint of this process, the depth where even the most optimally transmitted wavelength of sunlight finally encounters enough water molecules to be completely absorbed. Scientists have calculated this depth with remarkable precision. In the clearest ocean water, under perfect conditions, blue-green light at a wavelength of approximately 480 nanometers can penetrate to depths of about 12,000 feet before being reduced to essentially zero intensity. This isn't a theoretical limit. It's been measured, observed, and confirmed through countless oceanographic expeditions. We're floating at the absolute boundary of where sunlight, in any form, can reach. The mathematics behind this final absorption follow the same exponential decay curve we've been observing throughout our descent. But here we're witnessing its ultimate conclusion. Every foot of water we've passed through has absorbed its predictable percentage of the remaining light. Now, after 12,000 feet of this gentle, persistent absorption, we've reached the point where the percentage that remains has approached zero. But reaching this boundary doesn't feel like arriving at a wall or crossing a dramatic threshold. Instead, it feels like the natural culmination of a long, peaceful journey. The blue-green glow that has been our companion has been growing dimmer and dimmer, so gradually that we've barely noticed the change from moment to moment. Now, as we float in this deep water, we can sense that we've crossed into a realm where no external light source can ever penetrate. The water around us at this depth has characteristics unlike anything we might experience at the surface. The pressure here is nearly 400 times greater than atmospheric pressure at sea level, enough to compress air to less than 1% of its surface volume. The temperature hovers just above freezing, creating an environment that would be instantly fatal to most surface life forms. Yet this is not a dead zone. It's a realm where life has adapted to exist without any dependence on solar energy. The darkness here is not the simple absence of light that we might experience in a closed room or on a moonless night. It's something more fundamental: the complete absence of any electromagnetic radiation in the visible spectrum arriving from external sources. No photon that began its journey at the sun has ever reached this depth. The only light that exists here is what life creates for itself through the remarkable process of bioluminescence. This creates an environment that's unique in the known universe. While darkness exists in many places, in caves in the depths of space, in the interior of solid objects, nowhere else do we find this combination of complete solar darkness existing within a medium that can support complex life. The deep ocean represents a living laboratory for understanding how biological systems can function completely independently of solar energy. The creatures that inhabit this realm have evolved without any reference to the sun. Their biological clocks, if they have them at all, are not synchronized to the 24-hour cycle of day and night that governs surface life. Instead, they follow rhythms related to food availability, reproductive cycles, or the vertical migrations of prey species from shallower waters. They've developed entirely different relationships with time and energy. Many of the fish at this depth are what biologists call living fossils, species that have remained relatively unchanged for millions of years because their deep-sea environment has remained stable for such long periods. While surface environments have experienced ice ages, asteroid impacts, volcanic eruptions, and dramatic climate changes, the deep ocean has maintained its darkness, its cold temperatures, and its high-pressure environment with remarkable consistency. This stability has allowed for the evolution of some truly extraordinary adaptations. Many deep-sea creatures have lost their pigmentation entirely, appearing translucent or ghostly white in the sparse bioluminescent illumination. Others have developed elaborate light-producing organs called photophores, capable of creating complex patterns of bioluminescent display. Some have evolved enormous mouths and expandable stomachs, adaptations to a world where meals are scarce and unpredictable. The bioluminescent displays at this depth take on a different character than those we observed in the twilight zone above. Here, where no external light exists to compete with biological illumination, bioluminescence becomes the primary sensory modality. Creatures use light not just for communication or prey capture, but as a complete sensory system, creating their own illumination to navigate, hunt, and interact with their environment. Some deep-sea species have developed bioluminescent displays of extraordinary complexity and beauty. They can create patterns of light that flash in specific sequences, like Morse code written in living luminescence. Others produce steady glows that can be modulated in intensity and color. Some species have even evolved the ability to create different colors of bioluminescent light, using various chemical pathways to produce not just blue-green illumination, but reds, yellows, and even infrareds that are invisible to most other creatures. The chemical basis of bioluminescence involves a remarkable process where organisms convert chemical energy directly into light energy with extraordinary efficiency. The reaction typically involves a molecule called luciferin reacting with an enzyme called luciferase in the presence of oxygen and ADP. This reaction produces light with virtually no waste heat, a much more efficient process than any artificial light source humans have ever created. At 13,000 feet, we find ourselves in waters where this bioluminescent process has become the sole source of illumination. The complete absence of solar radiation creates an environment where biological light takes on profound importance. Every photon here was created by a living organism. Every flash of illumination represents a deliberate biological decision to expend energy, creating light. The energy costs of bioluminescence are significant for deep-sea creatures. In an environment where food is scarce and every calorie must be carefully conserved, the decision to create light represents a major metabolic investment. This means that bioluminescent displays in the deep ocean are never casual or accidental. They serve crucial functions that justify their energy costs. Some creatures use bioluminescence for counterlumination camouflage. They produce light on their undersides that matches the faint, downwelling light from above, making them invisible to predators looking up from below. Others use bioluminescence as a burglar alarm, creating bright flashes when attacked to startle predators or attract the attention of larger predators that might attack their attackers. The mating displays of deep-sea creatures often involve elaborate bioluminescent patterns. In the vast darkness of the deep ocean, finding a mate of the same species represents an enormous challenge. Bioluminescent displays serve as species-specific signals, allowing creatures to identify potential mates across the great distances of the deep sea. These displays can be incredibly complex, involving precise timing, specific color patterns, and intricate movement sequences. As we descend toward 14,000 feet, we enter what oceanographers call the abyssopelagic zone, where the pressure reaches nearly 450 times atmospheric pressure and the temperature remains just above freezing year-round. Here, the absence of solar radiation is so complete that it has shaped every aspect of the ecosystem. The food webs here are based entirely on organic matter that drifts down from the productive surface layers above, creating an economy based on what marine biologists call marine snow. This marine snow consists of the continuous gentle fall of organic particles from the upper ocean layers. Dead plankton, fecal pellets from surface animals, bits of larger organisms that have died and begun to decompose. This falling organic matter represents the primary energy input to the deep-sea ecosystem, the foundation that supports all life in these permanently dark waters. The journey of this organic matter from the surface to these depths can take weeks or months. As particles fall, they're consumed by creatures at intermediate depths, broken down by bacteria, and aggregated into larger particles. By the time organic matter reaches 14,000 feet, it has been processed and reprocessed many times, concentrated into the most energy-rich and easily digestible forms. The creatures that feed on this marine snow have evolved remarkable adaptations for capturing and processing these falling particles. Many have developed enlarged filtering structures, specialized feeding appendages, or modified digestive systems that can extract maximum nutrition from this sparse food source. Some species have evolved to follow the daily migration patterns of surface organisms, ascending towards shallower waters when feeding opportunities are best. At 15,000 feet deep, we find ourselves in an environment that represents the ultimate expression of life's independence from solar energy. Here, 3 miles beneath the surface, no photon that originated in nuclear fusion reactions that the sun has ever penetrated. The only energy sources are the chemical energy stored in organic matter falling from above and the chemical energy that organisms can extract from dissolved compounds in the seawater itself. Some bacteria at these depths have evolved the ability to derive energy from chemical processes that don't depend on organic matter at all. They can extract energy from dissolved hydrogen sulfide, methane, or other compounds, creating food webs based entirely on chemical energy rather than the solar energy that powers surface ecosystems. These chemosynthetic processes create oases of life around deep-sea vents and seeps, demonstrating that life can thrive in complete independence from the sun. The water itself at this depth has taken on characteristics that would be unrecognizable to surface dwellers. Under the enormous pressure, gas molecules are compressed to tiny fractions of their surface volumes. Dissolved gases behave differently. Chemical reactions proceed at altered rates, and even the basic properties of water itself are modified by the extreme conditions. Yet in this environment that seems so hostile to life, complex ecosystems flourish. Predator-prey relationships exist in intricate balance. Reproductive cycles continue across generations, and evolutionary processes continue to shape and refine species adaptations. The complete absence of solar radiation hasn't eliminated life. It has simply channeled life's creativity into different directions. The bioluminescent displays at this depth often take on an almost ethereal quality. In the complete absence of external light, every flash of biological illumination stands out with crystal clarity. The displays become more important, more elaborate, more carefully timed. Some species coordinate their bioluminescent activities, creating synchronized light shows that can be visible across surprisingly large areas of the deep sea. As we approach 16,000 feet, nearly 3 miles beneath the surface, we can reflect on the profound journey we've taken from the bright surface waters to this realm of eternal darkness. We've witnessed the complete transformation of a light-filled environment into one where illumination exists only as a creation of life itself. We've seen how the patient process of absorption, working molecule by molecule across thousands of feet of water, can completely exclude even the most persistent wavelengths of sunlight. The darkness here isn't a failure or an absence. It's an achievement. It represents the ocean's successful completion of a process that began with the first interaction between sunlight and seawater at the surface. Every photon that was absorbed during our journey contributed to the warmth of the ocean, became part of the energy budget that drives ocean currents and weather patterns. The transformation of light into heat wasn't a loss. It was a conversion of energy from one useful form into another. The creatures that live in this permanent darkness have achieved something remarkable: complete independence from solar energy while maintaining complex, sophisticated ecosystems. They've proven that life doesn't require sunlight to flourish, that biological creativity can find ways to thrive in environments that seem impossibly challenging. As we float here in this profound darkness, 3 miles beneath the surface, we can appreciate the elegant completion of our exploration of light absorption. We've followed the journey of photons from their birth in nuclear fusion reactions, through their travel across space, through their encounter with Earth's atmosphere, and finally through their gradual, gentle absorption by countless water molecules during their descent through the ocean. We've seen how the ocean's relationship with light creates some of the most stable, predictable, and beautiful physical processes on our planet. The darkness that surrounds us here isn't random or chaotic. It's the inevitable result of well-understood physical laws working with patient persistence across vast scales of space and time. The deep sea's eternal darkness teaches us about the power of gradual processes, about how small changes accumulated over great distances can create profound transformations. It shows us that even the most powerful forces, the light of our sun, can be gently but completely absorbed by something as simple as water, given enough time and space to work. In this place where blue finally surrenders, with a last wavelength of visible light gives up its energy to the embracing darkness, we find not an ending, but a transformation. The light hasn't been destroyed. It has been converted into heat, into motion, into the energy that drives the great circulation patterns of the ocean. The darkness here is alive with possibility, illuminated by the creativity of life itself, sustained by the endless falling of organic matter from the sunlit world above. As we continue our peaceful descent beyond the point where even blue light surrenders to darkness, we enter a realm where another fundamental force begins to reveal its profound influence on why the deep sea remains forever dark. Here, suspended 18,000 feet beneath the surface, more than 3 miles down, we encounter pressure in a way that few humans have ever experienced. This isn't the gentle pressure of a deep swimming pool or even the substantial pressure of a few hundred feet underwater. This is pressure as a fundamental force of nature, pressure that shapes not just the physical properties of water, but the very behavior of light itself. The pressure at this depth is truly extraordinary. Above us, 3.5 miles of water pressed down with a force that's over 500 times greater than the atmospheric pressure at sea level. To put this in perspective, imagine the weight of a large elephant balanced on every square inch of surface. That's the pressure that surrounds us here, pressing in from all directions with gentle but inexorable force. Yet somehow, this enormous pressure doesn't feel crushing or oppressive. Instead, it feels like being held, embraced, supported by something vast and stable. The water around us has a different quality than anything we might experience at the surface. It's denser, more substantial, almost solid in its presence. We're no longer floating through liquid, but suspended within something that feels more like liquid crystal. Perfectly clear, but with a weight and presence that's immediately apparent. This pressure affects every aspect of the deep sea environment, including the behavior of light itself. Under such enormous compression, water molecules are squeezed closer together than they would be at surface pressure. This increased density changes how electromagnetic radiation interacts with the water, subtly altering the absorption characteristics that we've been following throughout our journey. The relationship between pressure and light absorption is complex and beautiful. As water molecules are compressed closer together, their electron clouds, the invisible spheres of electric charge that surround each atom, begin to overlap slightly. This overlapping changes the energy levels at which electrons can absorb photons, fine-tuning the absorption spectrum of water in ways that wouldn't occur at surface pressures. Under the extreme pressure of 18,000 feet, water becomes slightly more efficient at absorbing certain wavelengths of light. The blue-green wavelengths that survived so persistently during our descent encounter water molecules that are more tightly packed, more energetically active, more ready to accept photon energy and convert it to molecular motion. It's as if the pressure itself is conspiring with the absorption process to ensure that no external light can penetrate to these depths. But pressure does more than just enhance light absorption. It also affects how any light that does exist, whether from bioluminescence or hypothetical external sources, behaves as it travels through the water. Light travels through pressurized water at a slightly different speed than it does through surface water. The refractive index of water changes under pressure, altering how light bends and focuses as it passes through the medium. These changes are subtle but measurable. The speed of light in water at 18,000 feet depth is about 1% slower than it is at the surface. This might not sound like much, but in the precise world of optical physics, even small changes in light speed can have significant effects on how illumination behaves in the environment. The pressure also affects the scattering processes that we explored in earlier chapters. Under extreme compression, suspended particles behave differently. Their scattering cross-sections change, and the overall efficiency of light redistribution is altered. The marine snow that creates such beautiful scattering effects in shallower waters is compressed here into denser, more compact particles that interact with light in subtly different ways. At 20,000 feet deep, we find ourselves in an environment where pressure has become one of the dominant physical forces shaping every aspect of existence. The pressure here is nearly 600 times atmospheric pressure, enough to compress air to less than 1/6 of 1% of its surface volume. Any gas bubbles that might exist at this depth are compressed to microscopic sizes, creating a liquid environment that's remarkably uniform and stable. This uniformity contributes to the optical properties of deep water in important ways. At the surface, variations in temperature, dissolved gases, and suspended particles create optical irregularities that can scatter and redirect light in complex patterns. But under the enormous pressure of the deep ocean, these variations are minimized. The water becomes more homogeneous, more predictable in its optical behavior. The temperature at this depth remains just above freezing, typically around 2 to 4 degrees Celsius. This near-freezing temperature, combined with the extreme pressure, creates conditions where water molecules move in slow, constrained patterns. They're still in liquid motion, but their movement is restricted by the compression and the cold. This creates a medium that's extremely stable optically, with minimal turbulence or variation that might affect light transmission. Under these conditions, any light that hypothetically reached this depth would encounter a medium that's almost perfectly designed for absorption. The water molecules are packed tightly together, moving slowly and predictably, ready to accept photon energy and convert it to heat. There are no optical irregularities to scatter light in unexpected directions, no turbulent mixing to create variations in absorption efficiency. It's as if nature has created the perfect, light-absorbing medium. The creatures that live under such enormous pressure have evolved remarkable adaptations that affect how they interact with light. Their body fluids must be at the same pressure as the surrounding water to prevent crushing, which means their internal chemistry operates under conditions that would be instantly fatal to surface organisms. These pressure adaptations also affect how they produce and perceive bioluminescent light. Many deep-sea organisms have evolved specialized pressure-resistant proteins that enable bioluminescence to function efficiently under extreme compression. The luciferin-luciferase reactions that create biological light must be carefully tuned to work under high-pressure conditions. Some species have evolved multiple versions of these proteins, each optimized for different pressure ranges they might encounter during vertical migrations. The photophores, light-producing organs, of deep-sea creatures are marvels of biological engineering that must function under crushing pressure. These organs often contain complex optical structures, lenses made of specialized proteins, reflectors created from crystalline structures, and filters that can modify the color and intensity of bioluminescent output. All of these structures must maintain their precise optical properties while compressed by enormous pressure. At 20,000 feet deep, we enter a realm where pressure begins to affect the fundamental chemistry of life itself. Here, over 4 miles beneath the surface, the pressure exceeds 650 times atmospheric pressure. Under such conditions, chemical reactions proceed at different rates. Protein structures are stabilized in unusual configurations, and even the basic properties of DNA and RNA are altered by the compression. These changes affect bioluminescence in fascinating ways. The chemical pathways that produce light must be modified to function efficiently under extreme pressure. Some deep-sea species have evolved pressure-activated bioluminescent systems that actually become more efficient as depth increases. Others have developed pressure-sensitive photophores that can adjust their light output based on the compression of their surrounding environment. The water itself at this depth has properties that would be almost unrecognizable to surface dwellers. Under such enormous pressure, water molecules are forced into configurations that don't exist at normal conditions. The hydrogen bonds between molecules are compressed and strengthened, creating a liquid that's denser, more viscous, and more structured than surface water. This highly structured water interacts with light in unique ways. The compressed molecular arrangement creates new pathways for photon absorption, new mechanisms for converting electromagnetic energy into molecular motion. The water becomes even more efficient at absorbing light, even more effective at ensuring that no external illumination can penetrate to these depths. The pressure also affects how sound travels through the water. And since both light and sound are forms of wave energy, there are interesting parallels between acoustic and optical behavior at these depths. Sound travels faster and farther in the compressed water of the deep ocean, creating an acoustic environment that's quite different from surface conditions. While this doesn't directly affect light transmission, it demonstrates how pressure can fundamentally alter the behavior of wave energy in the deep sea. As we descend toward 24,000 feet, nearly 5 miles beneath the surface, we encounter pressure levels that exceed 700 times atmospheric pressure. At this point, we're approaching the deepest parts of the ocean, the abyssal plains and deep trenches where pressure reaches its maximum values on our planet. The water here is compressed to a density that's significantly higher than surface water. This increased density affects every aspect of how matter and energy interact in this environment. Light photons, should any hypothetically reach this depth, would encounter a medium that's so efficient at absorption that even the most persistent electromagnetic radiation would be converted to heat within microseconds. But perhaps more importantly, the extreme pressure at this depth creates an environment that's remarkably stable and predictable. There are no dramatic temperature variations, no sudden changes in pressure or density, no turbulent mixing that might create optical irregularities. The deep ocean under extreme pressure becomes a kind of natural laboratory where the fundamental processes of light absorption can proceed with mathematical precision. The marine life at these depths has evolved under selective pressures that are literally measured in hundreds of atmospheres. Their biochemistry, their structural proteins, their bioluminescent systems. Everything has been refined through millions of years of evolution to function optimally under conditions that would instantly destroy most surface life forms. Some deep-sea species have evolved pressure-powered biological systems that actually use the compression of their environment as an energy source. These organisms can extract work from pressure differentials, using the enormous compression of the deep ocean to drive biochemical processes. While this doesn't directly relate to light production, it demonstrates the remarkable creativity of life in adapting to extreme pressure environments. The bioluminescent displays, at maximum depth, take on characteristics that are unique in the living world. Under extreme pressure, the chemical reactions that produce light are accelerated and intensified. Some species can produce bioluminescent flashes that are remarkably bright and efficient, taking advantage of the pressure-enhanced chemistry to create displays that would be impossible at surface conditions. At 26,000 feet deep, we find ourselves approaching the deepest accessible parts of the ocean. Here, in the Hadal Zone, named after Hades, the ancient underworld, pressure exceeds 800 times atmospheric pressure. The water is compressed to its maximum density, creating conditions that represent the ultimate expression of the ocean's ability to exclude external light. The Hadal Zone represents the completion of our journey through pressure's embrace. Here, every factor that contributes to light absorption has been maximized by the enormous compression. Water molecules are packed as tightly as they can be while remaining liquid. Chemical reactions proceed with pressure-enhanced efficiency. The medium has become perfectly optimized for converting any electromagnetic energy into heat. In this deepest realm, the pressure doesn't just enhance light absorption. It becomes an active participant in ensuring the permanent darkness of the deep sea. The compression creates molecular configurations that are impossibly efficient at capturing photon energy. Any light that could hypothetically penetrate to these depths would encounter a medium so perfectly designed for absorption that its conversion to heat would be immediate and complete. Yet despite the crushing pressure and permanent darkness, life thrives here. The deepest parts of the ocean host remarkable ecosystems based entirely on chemical energy, sustained by the fall of organic matter from the surface and the chemical processes that can extract energy from dissolved compounds. The extreme pressure that makes this environment so effective at absorbing light also creates unique opportunities for biochemical processes that don't exist anywhere else on Earth. The organisms that live under such extreme pressure have achieved something remarkable. They've created complex, sophisticated ecosystems that function completely independently of any external energy source. Their bioluminescent communications, their chemical-based metabolisms, their pressure-adapted biochemistry. All of it represents life's remarkable ability to thrive in conditions that seem impossible. As we float here in the crushing embrace of maximum oceanic pressure, nearly 5 miles beneath the surface, we can appreciate how pressure and light absorption work together to create the deep ocean's permanent darkness. The enormous compression doesn't just enhance the natural tendency of water to absorb light. It creates conditions where light absorption becomes so efficient that no external illumination could ever penetrate. The pressure at these depths represents more than just a physical force. It's an active participant in the ocean's ability to maintain its dark depths. Every aspect of the high-pressure environment contributes to ensuring that the deep sea remains forever separated from the solar energy that powers surface ecosystems. This separation isn't a barrier or an obstacle. It's a feature. The pressure-maintained darkness of the deep ocean creates opportunities for entirely different forms of life, different energy pathways, different evolutionary solutions. The crushing embrace of the depths doesn't destroy possibility. It creates new forms of possibility that couldn't exist anywhere else. In pressure's gentle embrace, we find not the harsh exclusion of life, but the careful maintenance of conditions that allow life to explore entirely different strategies for existence. The darkness maintained by extreme pressure becomes not an absence of opportunity, but a presence of alternative possibilities, alternative ways of organizing matter and energy into the complex patterns we call life. Here we are, suspended in the deepest reaches of our ocean planet, where pressure has perfected the art of light absorption and darkness reigns eternal. But as our eyes adjust to this liquid night, we begin to discover something remarkable. Darkness here doesn't mean emptiness. Instead, we find ourselves surrounded by one of the most extraordinary light shows on Earth, created entirely by life itself through the magical process of bioluminescence. In this realm where no photon from the sun has ever penetrated, where the crushing pressure has compressed water into the perfect light-absorbing medium, life has responded with creativity that rivals the aurora borealis. The creatures of the deep sea have become living stars, each one capable of producing its own illumination through chemical reactions that convert molecular energy directly into light with an efficiency that surpasses any technology humans have ever created. As we float here in this liquid cosmos, tiny points of blue and green light begin to appear around us like earthbound constellations. A jellyfish drifts past, its bell pulsing with waves of bioluminescent light that ripple across its translucent body in patterns that seem almost too beautiful to be real. The light it creates is pure and clean, a blue-green glow that matches perfectly the wavelength that once penetrated deepest from the surface, as if life has remembered the last color of sunlight and chosen to recreate it in the eternal darkness. The chemistry behind this living light is elegantly simple yet remarkably sophisticated. Deep within the cells of these creatures, molecules called luciferins react with enzymes called luciferases in the presence of oxygen and cellular energy. This reaction produces light through a process called chemiluminescence, where chemical energy is converted directly into photons with virtually no waste heat. It's like having molecular-scale light bulbs that can turn on and off instantly, requiring no external power source and producing no pollution. The efficiency of this biological lighting system is extraordinary. While a traditional incandescent light bulb converts only about 5% of its energy into visible light, with the remaining 95% lost as heat, bioluminescent reactions can achieve efficiencies approaching 100%. Every molecule of energy invested in the reaction produces useful illumination, making bioluminescence the most efficient form of lighting known to science. But efficiency alone doesn't explain the profound beauty of what we're witnessing. As we watch, a small deep-sea fish appears in the distance, its body outlined by a series of photophores, specialized light-producing organs that create a pattern of lights along its sides like the windows of a ship sailing through liquid space. These photophores can be controlled individually, allowing the fish to create complex patterns of illumination that serve multiple purposes simultaneously. Some of these lights serve as camouflage through a process called counterillumination. By producing light on their undersides that matches the faint bioluminescent glow filtering down from above, these fish can make themselves invisible to predators looking up from below. It's like wearing a cloak of light, perfectly matched to the optical environment, allowing them to move through the water column as if they were made of the same luminous medium that surrounds them. Other photophores serve as communication devices, creating species-specific patterns that allow creatures to identify potential mates in the vast darkness of the deep sea. In an environment where individuals might be separated by miles of empty water, these bioluminescent signals serve as beacons that can attract companions across enormous distances. Some species have evolved remarkably complex signaling systems, with different patterns indicating gender, reproductive readiness, territorial boundaries, or even individual identity. As we continue our observation, a larger creature appears, perhaps a deep-sea squid, whose entire body suddenly erupts in a cascade of flowing light. Waves of bioluminescence ripple across its skin like aurora patterns, creating a display so beautiful and otherworldly that it seems more like art than biology. This isn't random illumination, but a carefully controlled pattern, each flash and pulse serving a specific purpose in the creature's interaction with its environment. The colors of deep-sea bioluminescence are remarkably consistent across different species. Most produce light in the blue-green portion of the spectrum, the same wavelengths that once penetrated deepest from the surface. This isn't coincidence, but evolution's practical solution to the optical properties of seawater. Blue-green light travels farther through water than any other color, making it the most efficient choice for long-distance communication in the liquid medium. But some creatures have evolved the ability to produce other colors, creating bioluminescent displays that include reds, yellows, and even near-infrared wavelengths invisible to most other deep-sea species. These unusual colors serve as private communication channels, allowing species to signal to their own kind without alerting predators or competitors who can't see those particular wavelengths. The three-dimensional nature of bioluminescent displays in the deep ocean creates visual experiences that have no equivalent on land. Unlike terrestrial environments where most lighting comes from above, deep-sea bioluminescence can appear from any direction. Creatures can be above us, below us, to our sides, creating a spherical environment of potential illumination where light sources can appear anywhere in three-dimensional space. This omnidirectional lighting creates unique challenges and opportunities for deep-sea creatures. Predators must be aware that prey might approach from any direction, including directly above or below. Prey species have evolved the ability to detect bioluminescent light from multiple directions simultaneously, creating spherical fields of vision that allow them to monitor their entire surrounding environment for signs of danger or opportunity. The timing of bioluminescent displays reveals another layer of complexity in deep-sea ecosystems. Many species coordinate their light production with the daily migration patterns of surface organisms, even though they themselves live in eternal darkness. These vertical migrations bring nutrients and prey opportunities down from the surface layers, creating periods of increased activity in the deep-sea food web that are reflected in heightened bioluminescent activity. Some deep-sea creatures have evolved bioluminescent displays that are triggered by physical contact or disturbance. When touched or threatened, they produce brilliant flashes of light that can startle predators or attract the attention of larger predators that might attack their attackers. It's like having a biological burglar alarm that can summon help from unexpected directions. The energy costs of bioluminescence represent significant metabolic investments for deep-sea creatures. In an environment where food is scarce and every calorie must be carefully conserved, the decision to produce light is never made lightly. This economic constraint has driven the evolution of incredibly efficient bioluminescent systems and has shaped the behavior patterns of deep-sea species in profound ways. Many creatures have evolved the ability to control their bioluminescence with remarkable precision, turning photophores on and off like biological light switches. Some can modulate the intensity of their displays, creating dim glows for close-range communication or brilliant flashes for long-distance signaling. Others can control the duration of their light production, creating brief flickers or sustained illumination depending on their immediate needs. The development of bioluminescent capabilities has allowed deep-sea creatures to create complex social structures despite the vast emptiness of their environment. Schools of bioluminescent fish can coordinate their movements using light signals, creating synchronized displays that rival any choreographed performance. Mating rituals involve intricate light-based courtship dances, with potential partners responding to each other's displays and patterns that can continue for hours. As we observe this liquid light show, we begin to understand that bioluminescence serves functions that go far beyond simple illumination. It's a complete sensory and communication system that has allowed life to not just survive in the darkness of the deep ocean, but to thrive and create complex, sophisticated ecosystems that rival in complexity anything found in sunlit environments. The chemistry of bioluminescence varies remarkably between different species, with each group having evolved its own molecular solutions to the challenge of biological light production. Some species use bacterial symbionts, beneficial bacteria that live within specialized organs and produce light in exchange for nutrients and protection. Others have evolved their own cellular machinery for light production, creating photophores that function like biological LED arrays. The bacterial approach to bioluminescence creates some of the most stable and long-lasting biological light sources in the deep ocean. These symbiotic bacteria can produce continuous illumination for hours or even days, creating steady beacons that serve as permanent identity markers for their hosts. The relationship between host and bacteria represents one of the most successful partnerships in the biological world, with each partner contributing essential capabilities to their shared survival strategy. Self-produced bioluminescence, on the other hand, offers greater control and flexibility. Creatures with their own light-producing machinery can create complex temporal patterns, rapid flashes, and precisely timed displays that respond immediately to environmental stimuli. This cellular approach to bioluminescence has enabled the evolution of sophisticated signaling systems that function like biological Morse code. The energy costs of bioluminescence represent significant metabolic investments for deep-sea creatures. In an environment where food is scarce and every calorie must be carefully conserved, the decision to produce light is never made lightly. This economic constraint has driven the evolution of incredibly efficient bioluminescent systems and has shaped the behavior patterns of deep-sea species in profound ways. Many creatures have evolved the ability to control their bioluminescence with remarkable precision, turning photophores on and off like biological light switches. Some can modulate the intensity of their displays, creating dim glows for close-range communication or brilliant flashes for long-distance signaling. Others can control the duration of their light production, creating brief flickers or sustained illumination depending on their immediate needs. The development of bioluminescent capabilities has allowed deep-sea creatures to create complex social structures despite the vast emptiness of their environment. Schools of bioluminescent fish can coordinate their movements using light signals, creating synchronized displays that rival any choreographed performance. Mating rituals involve intricate light-based courtship dances, with potential partners responding to each other's displays and patterns that can continue for hours. As we observe this liquid light show, we begin to understand that bioluminescence serves functions that go far beyond simple illumination. It's a complete sensory and communication system that has allowed life to not just survive in the darkness of the deep ocean, but to thrive and create complex, sophisticated ecosystems that rival in complexity anything found in sunlit environments. The chemistry of bioluminescence varies remarkably between different species, with each group having evolved its own molecular solutions to the challenge of biological light production. Some species use bacterial symbionts, beneficial bacteria that live within specialized organs and produce light in exchange for nutrients and protection. Others have evolved their own cellular machinery for light production, creating photophores that function like biological LED arrays. The bacterial approach to bioluminescence creates some of the most stable and long-lasting biological light sources in the deep ocean. These symbiotic bacteria can produce continuous illumination for hours or even days, creating steady beacons that serve as permanent identity markers for their hosts. The relationship between host and bacteria represents one of the most successful partnerships in the biological world, with each partner contributing essential capabilities to their shared survival strategy. Self-produced bioluminescence, on the other hand, offers greater control and flexibility. Creatures with their own light-producing machinery can create complex temporal patterns, rapid flashes, and precisely timed displays that respond immediately to environmental stimuli. This cellular approach to bioluminescence has enabled the evolution of sophisticated signaling systems that function like biological Morse code. As we continue our exploration of this bioluminescent wonderland, suspended now in the deepest accessible regions of our planet's oceans, it's time to pause and truly understand the elegant physics that ensure these depths remain forever separated from the solar energy that powers the surface world. The mathematics behind this eternal darkness are as beautiful as they are precise, representing one of nature's most perfect demonstrations of how simple physical laws can create absolute boundaries. The journey we've taken from surface to these depths has followed what physicists call the Beer-Lambert law, though that formal name hardly captures the gentle poetry of the process we've witnessed. This law describes how light intensity decreases exponentially with distance through an absorbing medium, and in the case of seawater, it creates a mathematical certainty that no amount of surface illumination can ever penetrate beyond certain depths. To understand this certainty, let's consider the numbers that govern light absorption in seawater. Pure water absorbs light at different rates depending on wavelength, with red light being absorbed most readily and blue-green light least readily. The absorption coefficient for blue-green light in pure seawater is approximately 0.05 per meter, meaning that every meter of water absorbs about 5% of the remaining light. This might seem like a small percentage, but the power of exponential mathematics makes it decisive over large distances. After passing through 20 meters of water, blue-green light retains about 37% of its original intensity. After 40 meters, only about 14% remains. After 100 meters, less than 1% of the original light intensity survives. But our journey has taken us far beyond 100 meters. At the depths we've reached, 8,000 meters or more below the surface, the mathematics become truly extraordinary. The remaining light intensity would be reduced to 10 to the negative 174th power of its original value. To put this in perspective, this number is so small that if we started with all the light energy produced by every star in the observable universe, after passing through 8,000 meters of seawater, the remaining intensity would be far too small to detect with any conceivable instrument. This isn't just theoretical darkness. It's mathematical proof that certain depths of the ocean exist in absolute separation from solar energy. The exponential nature of light absorption creates boundaries that are more definitive than any physical wall, more absolute than any barrier humans have ever constructed. The wavelength dependence of this absorption process creates what scientists call the optical window of seawater, the narrow range of blue-green wavelengths that penetrate deepest into the ocean. This window peaks at approximately 480 nanometers, the exact wavelength that we observed persisting longest during our descent. The physics of molecular absorption have selected this particular color as the ocean's preferred wavelength, the one that travels farthest before surrendering to the patient embrace of water molecules. But even this most penetrating wavelength faces inevitable defeat when confronted with enough water. The absorption coefficient for 480 nanometer light in pure seawater means that 99.99% of such light is absorbed within the first kilometer of depth. The remaining 1% continues downward, but faces the same absorption rate in each subsequent layer, ensuring its eventual complete elimination. The purity of seawater affects these calculations significantly. The numbers we've been discussing apply to the clearest possible ocean water, found only in certain remote regions where dissolved organic matter and suspended particles are at their absolute minimum. In most ocean areas, additional absorption and scattering by dissolved substances and particles reduce light penetration even further. Dissolved organic compounds, many of them yellow or brown in color, add their own absorption characteristics to the water. These substances, collectively called color-dissolved organic matter or CDOM, preferentially absorb blue and ultraviolet light, further reducing the penetration of short wavelengths into the deep ocean. Their presence shifts the optical window toward longer wavelengths and reduces the overall transparency of the water. Suspended particles add both absorption and scattering to the optical properties of seawater. Even in the clearest ocean water, microscopic particles are always present. Bits of organic matter, microscopic organisms, tiny fragments of calcium carbonate, particles of clay. Each of these contributes to reducing light penetration, ensuring that the mathematical limits we've calculated represent the absolute best-case scenario for light transmission. The temperature and pressure variations we've encountered during our descent also affect the optical properties of seawater in subtle but measurable ways. As water temperature decreases and pressure increases with depth, the molecular structure of water changes slightly, altering its interaction with electromagnetic radiation. These effects are small compared to the fundamental absorption characteristics of water, but they contribute to the overall efficiency of light absorption in the deep ocean. The salinity of seawater adds another layer of complexity to the absorption process. Dissolved salts, particularly sodium chloride, modify the electronic structure of water molecules and change their absorption characteristics. The presence of dissolved ions creates additional pathways for photon absorption, further enhancing the ocean's ability to convert light energy into heat. But perhaps most remarkable is the self-reinforcing nature of the deep ocean's darkness. As light is absorbed and converted to heat, it contributes to the thermal structure of the ocean, which in turn affects water density and circulation patterns. These circulation patterns transport dissolved organic matter and particles, which further reduce light penetration. The ocean's optical properties help create physical conditions that enhance those same optical properties, creating a stable system that maintains its dark depths with remarkable consistency. The mathematical certainty of deep ocean darkness has profound implications for our understanding of energy flow in marine ecosystems. While surface ecosystems can rely on a constant input of solar energy, deep-sea ecosystems must operate on entirely different principles. The exponential absorption of light creates a sharp energy boundary that divides the ocean into two fundamentally different realms. The sunlit surface layers where photosynthesis is possible, and the dark depths where all energy must come from other sources. This energy boundary is remarkably stable over geological timescales. The fundamental physical properties that create the ocean's optical characteristics, the absorption spectrum of water, the molecular structure of seawater, the behavior of electromagnetic radiation in liquid media, are constants that don't change significantly over millions of years. This means that the deep ocean has maintained its essential darkness for as long as liquid water has existed on Earth. The physics of light absorption in seawater also explain why the ocean depths are so thermally stable. As light energy is absorbed and converted to heat throughout the water column, it contributes to the ocean's thermal budget in predictable ways. The exponential nature of light absorption means that most solar heating occurs in the upper layers, creating the temperature gradients that drive ocean circulation while leaving the deep waters in thermal as well as optical isolation. Understanding these physical principles helps us appreciate why life in the deep ocean has evolved such radically different strategies from surface life. The mathematical certainty of eternal darkness has created evolutionary pressures that favor entirely different approaches to energy acquisition, sensory perception, and ecological interaction. The physics of light absorption hasn't just created dark water. It has created the conditions for entirely different forms of life. The wavelength selectivity of water absorption also explains the convergent evolution of bioluminescence in deep-sea creatures. The The fact that blue-green light penetrates deepest into the ocean means that any biological light production in these depths is most efficient when it operates at these same wavelengths. Evolution has independently discovered the same optimal wavelengths that physics predicts for maximum transmission through seawater. As our journey through the ocean's eternal darkness draws toward its gentle conclusion, we find ourselves suspended in a place that exists nowhere else in the known universe. A realm where complex life flourishes in complete independence from stellar energy, where darkness has become not an absence, but a presence, not a void, but a foundation for entirely different forms of beauty and complexity. Here, in these deepest accessible regions of our planet's oceans, we've witnessed something remarkable. The transformation of what might seem like the most hostile environment imaginable into one of Earth's most stable and enduring ecosystems. The crushing pressure that would instantly destroy most surface life has become a gentle, constant embrace. The eternal darkness that might seem like emptiness has revealed itself as a canvas for living light more beautiful than any aurora. As we drift slowly through this liquid cosmos, surrounded by the gentle sparkle of bioluminescent life, we can reflect on the profound journey we've taken together. We began at the surface, where sunlight painted the ocean in the full spectrum of colors, where the energy of our nearest star created a world of warmth and abundance and familiar illumination. We descended through layers where that light was gradually, patiently transformed, where each foot of depth added its contribution to the gentle process of absorption that has been occurring unchanged for billions of years. We observed the dance of photons and molecules, the elegant chemistry by which electromagnetic energy becomes thermal energy, the mathematical precision of exponential decay playing out in the patient transformation of light into heat. We witnessed the final surrender of even the most persistent wavelengths, the completion of a process that began 93 million miles away in the nuclear fires of the sun and concluded here in the gentle embrace of water molecules. But we discovered that this surrender wasn't an ending. It was a beginning. In the absence of external light, life created its own illumination, transforming the eternal darkness into a realm of biological stars, living constellations, creatures that paint patterns of light against the liquid night with an artistry that rivals anything in the cosmos. We learned that bioluminescence isn't just a substitute for sunlight. It's an entirely different approach to illumination, one that's more efficient, more controllable, more beautiful than any technology humans have ever created. The deep ocean's darkness taught us about boundaries and transformations, about how even the most powerful forces eventually find their limits and their peace. We saw how the relentless energy of sunlight, after traveling across the vastness of space and penetrating miles of water, finally comes to rest in the gentle warming of seawater molecules. We learned that absorption isn't destruction, but conversion, that the light doesn't disappear, but becomes part of the ocean's thermal structure, contributing to the currents and weather patterns that affect the entire planet. We discovered that pressure, which might seem like a crushing force, actually creates some of the most stable and peaceful environments on Earth. The enormous compression of the deep ocean creates water with remarkable optical properties, eliminates turbulence and variation, and provides a constant, reliable environment where life can evolve and thrive over geological timescales. In Pressure's embrace, we found not destruction but preservation, not chaos but order. The creatures we encountered in these depths revealed life's remarkable creativity in adapting to conditions that seem impossible. From the bacterial symbionts that create steady biological light sources to the complex photophore arrays that allow precise control of bioluminescent displays, from the pressure-adapted proteins that enable biochemistry under crushing compression to the enlarged eyes that gather every available photon. Each adaptation represents millions of years of evolutionary refinement, life finding elegant solutions to extraordinary challenges. We learned about the mathematics of darkness, the beautiful precision with which physical laws create absolute boundaries between the sunlit surface and the eternally dark depths. The exponential absorption of light by seawater isn't just a physical process. It's a natural law that has shaped the evolution of life on our planet, creating two fundamentally different realms with their own energy sources, their own ecological principles, their own forms of beauty. Perhaps most importantly, we discovered that darkness isn't empty. The deep ocean's eternal night is filled with possibilities that don't exist anywhere else. Forms of life that couldn't survive in the presence of sunlight. Ecological relationships based on entirely different principles. Communication systems that use living light to create messages more complex than any human language. As we float here in this gentle darkness, surrounded by the slow drift of marine snow and the occasional sparkle of bioluminescent display, we can feel ourselves becoming part of this ancient ecosystem. The water that supports us has been moving through these depths for centuries, carrying nutrients and dissolved compounds from distant shores, connecting the deepest ocean basins in slow, grand circulation patterns that span the globe. The darkness that surrounds us connects us to the fundamental physics of our universe, to the way energy and matter interact across scales from the molecular to the cosmic. We're experiencing firsthand the limits of stellar influence, the boundary where the sun's reach finally ends and other forms of energy take over. We're witnessing the place where the electromagnetic spectrum surrenders to biochemistry, where fusion energy from the solar core finally transforms into the gentle warmth of deep seawater. The pressure that embraces us connects us to the fundamental forces that shape planets, to the way gravity and matter interact to create the extreme environments where life pushes the boundaries of what's possible. We're experiencing conditions that exist nowhere on the surface of our planet. Conditions that might be common on water worlds orbiting distant stars. Conditions that teach us about the remarkable resilience and adaptability of life itself. The bioluminescent displays we've witnessed connect us to one of the most beautiful phenomena in the natural world, to the way life can create light through chemistry, to the evolution of communication systems that use photons as messages, to the development of ecosystems based entirely on biological energy sources. We've seen living light that's more efficient than any human technology, more beautiful than any artificial display, more purposeful than any engineered system. As our exploration draws to its peaceful conclusion, we can carry with us the profound lessons of the deep ocean's eternal darkness. We've learned that limits aren't limitations, but opportunities for creativity. We've seen that the most extreme environments can support the most extraordinary life. We've discovered that darkness and light aren't opposites, but different expressions of the same underlying energy, different points on a spectrum that includes countless gradations of possibility. The deep ocean's permanent darkness reminds us that our planet is far more diverse, far more creative, far more full of unexpected beauty than we might imagine from our surface perspective. Beneath the familiar world of sunlight and weather, of day and night, of seasons and storms, lies another world entirely. A world of living stars and patient chemistry, of pressure-adapted life and bioluminescent art, of thermal stability and eternal night. This other world operates on different principles, follows different rhythms, creates different forms of beauty, but it's not separate from our surface world. It's connected to it through the falling of marine snow, the circulation of ocean currents, the migration of creatures between depths, the fundamental physics that govern energy and matter throughout our planet. As we begin our gentle ascent back toward the sunlit world above, we carry with us the memory of this liquid cosmos, this realm where darkness has revealed itself as a canvas for forms of life and beauty that exist nowhere else. We've seen how the patient absorption of sunlight creates the conditions for entirely different forms of illumination. We've learned how the crushing force of pressure creates some of the most stable environments on Earth. We've discovered how the absence of external energy sources has driven the evolution of the most efficient biological lighting systems in the known universe. The deep ocean's eternal darkness has taught us about persistence and transformation, about limits and creativity, about the way life finds opportunities in the most challenging conditions. As we slowly rise through the layers we descended, we can appreciate each level of filtered light we encounter, each gradation of illumination that marks our return to the surface world. But we'll never forget the profound beauty of the depths, the gentle embrace of pressure, the living stars of bioluminescence, the patient chemistry of light absorption. We've been privileged to explore one of the most remarkable environments on our planet, to witness processes that have been occurring unchanged for billions of years, to observe life forms that represent entirely different solutions to the challenges of existence. Sleep well, fellow explorer of the depths. Let the memory of those living lights dance gently behind your closed eyes. Let the patient rhythm of deep currents slow your breathing. Let the gentle embrace of pressure ease your muscles into peaceful rest. Let the profound darkness of the deep ocean carry you into dreams where light and shadow dance together in patterns as beautiful as bioluminescence, as gentle as the eternal night of the deepest sea. Thank you for joining me on this peaceful journey into the ocean's heart. If these gentle explorations of science have brought you comfort, if the wonder of the deep sea has helped ease you toward rest, I'd be grateful if you'd consider subscribing to Sleepy Science Hub. Share your thoughts in the comments below. Where in the world are you drifting off to sleep tonight? And what aspects of the deep ocean's eternal darkness spoke most peacefully to your mind? Until our next exploration together, may your dreams be as vast and mysterious as the deepest ocean, as gentle as the pressure that embraces these liquid depths, as beautiful as the living lights that paint the darkness with their patient, eternal glow.